Hey everyone, welcome to this explainer. Today we're taking on one of the most famous, fundamental, and frankly intimidating concepts in all of science, the Schrodinger wave equation. If you've ever wanted quantum physics explained in a way that actually makes sense, you are in the exact right place. We're going to go on a journey from mystery to mastery today, breaking down the exact mathematics that govern the microscopic world. We'll be diving into wave-particle duality, atomic orbitals, and exactly how the Schrodinger equation works.
Okay, let's dive into this. Here is our roadmap. We'll quickly cover when classical physics fails, look at matter as a standing wave, explore the quantum F equals ma, decode the wave function, figure out why imaginary numbers matter, and finally wrap up with the concept of a probabilistic universe.
Right, Section 1. When classical physics fails. To really grasp the quantum realm, we first need to see exactly where our classical understanding of reality just broke down. Think back to the early 20th century. It was a time of a rapid, massive paradigm shift in theoretical physics. In 1905, Planck and Einstein basically forced the scientific community to accept that energy comes in discrete little packets, quanta, and that light exhibits wave-particle duality. Fast forward a bit to 1923, and Louis de Broglie drops a total bombshell. He proposed that this duality extends to all matter, meaning literally everything has a wavelength. And then just 2 years later, during a winter holiday in the Swiss Alps, Erwin Schrödinger took that radical idea and formulated the mathematical foundation for quantum mechanics. Now, you might be looking at your own hands right now and thinking, well, I don't exactly feel like a wave. And you'd be absolutely right. An object's wavelength is inversely proportional to its mass. Because you, or even a tiny molecule, have so much mass compared to an atom, your wavelength is incredibly small. It's completely negligible. But an electron has an unimaginably tiny mass, so its wave nature is highly relevant. Its wavelength is roughly the size of an atom itself. At that macroscopic scale, we simply have no choice but to view the electron as both a particle and a wave. Let's move to Section 2 and see how this builds, specifically looking at matter as a standing wave. It really helps to compare two different types of waves here. Think of a classical standing wave, like a plucked guitar string. It's fixed at both ends, right? It vibrates in the middle, but the ends don't move. But a quantum matter wave is entirely different. It wraps around in a circle, completely surrounding an atomic nucleus. And that is exactly how we have to start visualizing an electron. And this brilliantly illustrates a key rule. For a circular standing wave to perfectly connect with itself and actually exist, it must have an exact integer number of wavelengths. 1, 2, 3, and so on. You can't have 2.5 wavelengths, because then the wave would just destructively cancel itself out. And since increasing the number of wavelengths increases the wave's energy, the electron can only inhabit specific, discrete energy levels. This right here is the very foundation of atomic orbitals and the Bohr model of the atom. It's like a giant puzzle perfectly clicking into place. Okay, moving on to Section 3. Let's look at the actual equation Schrödinger developed to model all this weird wave behavior, the quantum F equals ma. To give you a really simple explanation of the Schrödinger equation, let's compare it to something super familiar. In classical systems, if you want to know everything about, say, a baseball's trajectory, you use Newton's second law, force equals mass times acceleration, F equals ma. Well, in quantum systems, Schrödinger's equation plays that exact same fundamental role. It is the absolute starting point. But instead of giving us a definitive, clear physical trajectory, it solves for a three-dimensional wave function, which we represent with the Greek letter psi. Now, the actual math involves some pretty heavy calculus, but the core concept is absolutely beautiful in its simplicity. A massive part of the equation is what's called the Hamiltonian operator. Don't let the fancy name scare you off. It simply represents a set of mathematical operations detailing all the physical interactions affecting the system. At its heart, it's really just saying that the kinetic energy of the particle plus its potential energy equals its total energy. Let's test this out with a classic physics thought experiment, the particle in a 1D box. Imagine an electron trapped between two infinitely thick, impenetrable walls, where the potential energy outside those walls is infinite. Because the particle can never ever exist inside or past those walls, the wave function, psi, must be exactly zero at the boundaries. Just like our guitar string from earlier, only perfectly fitting sine waves can exist between these walls without breaking the mathematical rules. So the physical constraints of the box literally force the math to only allow specific quantized energy states.
All right, Section 4, decoding the wave function. Let's talk about that mysterious Greek letter psi.
So what is it? The wave function is a mathematical tool. Think of it as the ultimate information container for a quantum system. If you solve the Schrodinger equation and find psi, you have unlocked absolutely everything there is to know about that particle's possible position, momentum, and energy. But, and this is a big but, the wave function itself isn't exactly a physical object you can touch. It's pure math. So the crucial point is how we actually connect this abstract math to physical reality. In 1926, a physicist named Max Born proposed what we now call the Born rule. He realized that if you take the wave function and square its magnitude, you get the probability density. It doesn't tell you exactly where the electron is right now. Rather, it tells you the exact probability of finding the electron in a particular location if you were to actually measure it. If we map out the probability for the lowest energy state of our particle in a box, it looks something like this. The wave function peaks right in the middle and goes to exactly 0 at the walls. Because of this, squaring it gives us this neat probability curve. It means you are highly, highly likely to find the electron right in the center of the box, and you have absolutely 0 chance of finding it inside the walls. Moving into section 5, this is where things get really counterintuitive. Why imaginary numbers matter. Yep, we're talking about the imaginary number I, the square root of -1. You really have to ask, what is a completely imaginary number doing at the very core of a physics equation that describes real physical matter? Up until this point in history, physicists used imaginary numbers as neat mathematical tricks to make calculations easier, sure, but the final physical answer was always a real number. Well, Schrödinger's equation changed that forever. Now, what's really interesting about this slide is how the equation operates. In the time-dependent Schrödinger equation, the spatial curvature of the wave tells us how it should move, but I effectively acts as the engine. When you multiply a value by I on the complex plane, it rotates it by exactly 90 degrees. So as the equation calculates forward in time, I continuously rotates the spatial derivative of the wave function. It drives it forward not as a simple up and down wave, but as a spinning, spiraling, complex wave. And this isn't just a clever math trick. It has profound implications for reality. Those imaginary numbers encode the phase, or the angle, of the wave function. And because these matter waves have a complex phase, they can interact with each other. If the peaks and troughs of two matter waves are out of phase, they can actually cancel each other out through destructive interference. This invisible complex phase is exactly what causes electrons to create wavy barcode-like interference patterns in the famous double-slit experiment, instead of just landing in two solid clumps. Which brings us to our final section, Section 6, a probabilistic universe. This stuff is so weird that even the historical titans of quantum mechanics found it astounding. Take Paul Dirac, one of the greatest physicists of the 20th century. He noted that these probability amplitudes are the source of all interference phenomena, but he frankly admitted that their physical significance is, quote, obscure. Nature essentially hides its true underlying mechanics in these complex probabilities. So, to summarize the sheer magnitude of this explainer, the Schrödinger equation computes completely deterministically. The math is rigorous, predictable, and precise. But the final result it gives us is fundamentally probabilistic. Electrons don't exist as tiny solid billiard balls zooming around. They exist as smeared out clouds of probability density. How we actually interpret that reality, whether through the Copenhagen interpretation where the wave collapses upon measurement, or the many worlds interpretation where every possibility plays out in a branching multiverse, is literally still an open question. Schrödinger's equation permanently shattered the old Newtonian idea of a perfectly predictable clockwork universe. It proved that at the most fundamental level, the universe is built on chance, waves, and complex numbers. So I'll leave you with this. If the very foundation of the matter making up your body, the screens are looking at, and the stars in the sky is governed by a complex, probabilistic wave, what does that actually mean for the true nature of reality? Think about that, keep questioning everything, and keep learning.